In the previous video segment, we looked at Newton-Euler methods applied in a brute force method to separated individual bodies of a multi-body system. In this video segment, we're discussing a much more elegant way of essentially looking at projected Newton-Euler methods, which directly include the kinematic relationship of these individual bodies that are interconnected in a multi-body system. So what we're going to do here is we are applying Newton-Euler, but instead of applying it for an individual body which can move in an arbitrary direction rotation, we are looking at the generalized motion directions. So let's start with the formula that we derived in the introduction video segment of today's lecture, where we said essentially to have dynamic equilibrium, we have to have this the virtual work part being 0, which was nothing else than the pre-multiplication of virtual displacements, which are displacements in positions and displacements in rotations, multiplied with the change in impulse minus external forces and the change in angular momentum minus external torques, and this multiplication here has to be 0. Now for a single body, we had this component here. The variation in position and rotation could be chosen arbitrarily because this individual body can be moved in all directions without constraints. That means if this whole thing has to be 0, we had to have that part to be 0. Now this is not true anymore for interlinked multi-body systems, where we have essentially the variation that needs to be consistent with the individual joints. So if I have two bodies which are connected through a rotary joint, obviously I cannot arbitrarily choose the displacement of body 1 and body 2. I have to choose them such that they're consistent with this individual link joint that is in between. And this is what we're going to do here. So we have to first formulate what are variations in position rotations which are consistent with the joints that we have in this multi-body system. And to do so, we're going to go back to generalized coordinates, which we essentially introduced as a way to describe the motion with a minimal set of parameters. So what we have to do is we express impulse and angular momentum as a function of generalized coordinates. So what do we need for this? As we know, impulse is a function of velocity, so we need to express linear and angular velocity as a function of q dot, and we have to do the same thing for linear and angular acceleration, which is a function of q double dot and q dot. And as we have learned, the mapping between joint space, so q's, to task space, which are velocities of a point, we have nothing else than the Jacobians in between. So all we need is position and rotation Jacobians. And if we take the time derivative of that, we see that we have first, this is j times q dot. So what we need is j times q double dot and j dot times q dot. So that's the simple derivation rule of a product. Then we can use this in order to express the change in linear impulse and the change in angular momentum, which is mass for linear direction, mass times acceleration, and for rotation direction we have inertia times rotation, angular acceleration plus this cross-coupling term. And we're expressing now all these individual components that we have in here as a function of generalized coordinates, generalized velocities, and generalized accelerations. So we have acceleration, which is nothing else than js times q double dot plus j dot times q dot. So that's my first line here. And I do the same thing for the angular direction. So we have angular acceleration, which is given here. I insert this here, so I have the rotation Jacobian times q double dot plus the time derivative of the rotation Jacobian times q dot, and then I have the cross-coupling term, and also here I replace this omega here with this formula of omega being nothing else than rotation Jacobian times my q dot. So in other words, I have now a description of change of linear impulse and change of angular momentum, which is only depending on mass properties of the system, so these m's and these inertias, and Jacobians, and q dots, q double dots. And now what I do is I move this formulation that I have up here, which is variations in position and rotations, to variations in generalized coordinates. So I express my variation in position as a function of variations in generalized coordinates. And similar to what we've seen before, instead of like time differentiation, we have now variations, but the mapping between joint and task space remains through this Jacobian. So we have the same formula here. So with this, I can rewrite this thing up here, which is, we have dynamic equilibrium, so this must be 0. And what I do express is this component here I replace with this formula. So what I have is, I have this transposed, so I have to change order. I have my virtual displacement in Q transposed, then I have this part here, and I exchange now, for the position I take S, so I take my center of gravity, so S represents my center of gravity because that's going to be important later. So we have this part here, and then we inject here the time derivative of linear and angular momentum, which is nothing else than this formula that we have here, which goes in here. And then we have the last part, which is the external forces, which is here, again pre-multiplied with the transposed of the Jacobians, which comes in from that thing here. So now we have the description of something that must be 0 while we're only varying in Q. Now what is important to understand is that because we choose Q as this generalized coordinates describe the motion, joint space motion of a system, this has to be true now for an arbitrary variation in Q, because the selection of Q is such that any motion there is already consistent with the individual joint constraint. So we have now this formula which has to be true for any Q dot. So in other words, this part here must be 0. And what we see in here are the individual components of mass matrix, of Coriolis and centrifugal parts, and of gravitational parts. So something times acceleration, then this coupling term, which is depending on the configuration and on velocity, and then the gravity part with the external forces being m times g. To sum this up, what we have derived now is the equations of motion in the form of mq double dot plus b plus g equal to 0, so dynamic equilibrium, where these mass matrix, Coriolis, and gravitational parts are given through this formula that we have here. And what is important to see in this formula is all I need to have are Jacobians of a center of gravity position of all individual bodies. So I sum up over all the bodies the Jacobian of the center of gravity, same here, rotational Jacobian of that bodies, and I multiply them with masses and inertia tensors. And similar to that also for the Coriolis part and centrifugal part, in here I have Jacobians, I have time derivatives of these Jacobians, and that's it. And the same for gravity. Now there's one last element that I pointed out here in color. If you remember, Jacobians always have a basis. So we have here a basis, while m so this mass matrix, this essentially is in this generalized space, right? So it multiplies with generalized coordinates. That means all we need to ensure is that this mapping that happens here, so the mapping between joint and task space, is always individual contributions of this mapping have to have the same basis. So I can map the linear part and the rotational part from different base frames, but within individual contributions, they must be the same basis frame. Now, small add-on here, if you have an actuated system, we include actuation forces as external forces to each body. And if this actuator acts in the direction of generalized coordinates, this tau that we introduced there really corresponds only to the stacked actuator. But you're going to see this later on in examples much more straightforward. Now, to conclude this video segment, we're going to do the exact same problem that we have looked at before using the free cut method, but now using the projected Newton-Euler method. So we have this card pole pendulum here on the right with a card where we attach a pendulum to it. But now what we're applying here is, and I give you here, what we're doing is first to introduce generalized coordinates. So we have our q equal to x and phi. Then you have to define, figure out the position vectors as a function of this q, angular velocities as a function of these generalized velocities, and the Jacobians. And we know how to do all of that. So this is like a straightforward procedure that we learned in the kinematic section. And we can just then apply this method and move on to write down the dynamics equations of motion.